This talk is about the good old times. We'll touch, well, almost everything from the old C64. And, well, just let's start. Give a hand to Michael Steil.
Hi. Okay, hi. So, hello, I'm going to talk about the Commodore 64. You may or may not be here because of the whole retro wave. Retro is cool, everyone does emulation, runs C64 on their X serves, has a C64 in their office next to the Mac Pro. There are people who even have license plates with Commodore 64 references. But there's a very important point I want to make here, which is you can do good chip design and bad chip design. And the C64 was a very good chip design. If you compare it to competitors from the same time, like IBM's CGA card, it could address the same amount of memory, but could do graphics like this, and the Commodore could do graphics like that, or with tricks even like that. And the other thing is you can be dumb or you can be creative about coding, and if you have to do cycle exact coding, there's so much you can do, and the question is this an art that has been lost? So I'm going to talk a bit about that kind of programming a machine. These are the topics that I'm going to address. I have 64 minutes and I have 256 slides. Commodore was founded in 1954 by Jack Tramiel. That's what he looks like today. They made calculators and later bought the company MOS Technology, which is a chip manufacturer. Engineering was headed by Chuck Peddle. This is what he looks today. They made the 6502 CPU originally intended for industrial control, but they also made the KIM-1, which is a computer kit based around the 6502. Commodore thought it would be a good idea to extend that design into a home computer, so the Commodore PET was sold for small businesses and the education market, but they also targeted the home computer business with the Commodore VIC-20, which was a very, very stripped-down computer system, and its successor, the Commodore 64, with 64 kilobytes of memory, which was a lot back then, if you compared it to the market, which was well over $1,000 if you wanted 64 kilobytes of RAM. This is all just the machine, not the monitor or the disk drive. And C64 that sold for just $595 US. There was a successor to the C64, the C128, which was compatible, so it sold pretty well, and the Plus 4, incompatible and didn't sell that well. Between 1982 and 1994, they sold 17 million C64s, so this makes it the best-selling computer of all times, plus there's an extra 3 million C128s. This is what a C64 looks like. There are several models of it. This is the original one. They made an updated, flat version of it and went back to the original design because it was cheaper. They made a golden version, limited edition. They made a portable version, and they made that one. So this is what it looks like if you start a C64. It boots right into BASIC, just from ROM. You can either type in your BASIC program if you want, or you can load something from disk or tape. To give you an impression on the graphics capabilities, this is a very, very early demo by Commodore themselves, the 1982 Christmas demo. Later demos looked more like this, and even later, more modern demos had pretty good graphics, did some 3D effects, or did some other very impressive stuff. Very early games, like Lode Runner, looked like this. Later games looked a little more complex, or even later games used screen modes that weren't originally possible. All on the same unmodified hardware. So let's look at the C64 from the outside first. On the right-hand side, you have two control ports. You can either attach two joysticks or a joystick and a mouse. On the back, you have the expansion port. You can attach pretty much anything there because the whole CPU bus is exported there. Any extension hardware. Mostly people attached extra ROMs there with library routines and extra basic extensions for usability, like the final cartridge on this picture. There's two monitor connectors, one RF connector and an S-video-like connector for monitors. The IEC serial bus for floppy drives and printers, tape connector, and the user port for pretty much anything else. So this is what a typical system would look like, a C64 and a 1541 disk drive on a Commodore monitor in this case. Looking inside, this is the main board. On the left-hand side, you have the CPU, which is a 6510, which is very similar to the 6502. Two CIA 6526 controllers. These are I/O controllers. And on the right, you have the SID 6581 sound chip and the VIC video chip. So let's go through all these components and let me explain them to you a little bit. The 6502 was designed in 1975 by a team of engineers that had been at the company Moss. They had left Motorola. Engineering was headed by Chuck Peddle, and they are holding the die shot there. The schematic diagram of it, you'll understand it in 5 minutes. This should give you an impression of what the assembly language looks like. Assembly instructions are 1 up to 3 bytes, so it's a 1-byte opcode and 0 to 2 bytes operand. It's an 8-bit CPU, it has 3 registers, the accumulator, which can do arithmetic and logic, 2 index registers, X and Y. They can be used for indexing, can't do arithmetic, but they can be incremented and decremented. There's a processor status with negative overflow 0 and carry and a few other bits, 16-bit program counter, and an 8-bit stack pointer or an 8-bit stack pointer register and an effective 16-bit stack pointer. The upper 8-bit are always confined to 1. So this has some implications on the memory layout of a 6502-based system. The page 0 in RAM is special. I'll talk about this one later. Page 1 is the stack, so the stack is always confined to those 256 bytes. The stack starts at 01FF and grows down. This is an overview of the opcodes that it supports. Out of a possible 256 opcodes, about 150 are available. Let me give you an impression on the instruction set. There are load instructions, store instructions of those registers. You can rotate and shift only the accumulator. You can increment and decrement memory and the X and Y registers. There's addition and subtraction instructions. They always add or subtract the carry as well, so you have to explicitly set or clear the carry. There's Boolean logic, there's compare, and there's the bit instruction. So all these load from memory or from registers, all these are the store instructions. There are some that do direct memory, read, modify, write. These are the arithmetic ones, these are the logic ones, and the column on the left are just like those on the right, but they only change the bits instead of writing back the result. For all those instructions, there are several addressing modes. So depending on which instruction, there are either more or less addressing modes available. The first one I want to talk about is the immediate addressing mode. It's available for pretty much every, or for all the load instructions. You have the hash sign there that signals that it's an immediate load. And what it does is it just puts the value of 17 into the accumulator in this example. Absolute addressing is a memory read, so I have a 2-byte operand, 16-bit operand, so it's encoded with these 3 bytes, as you can see there. And what happens there, I read from 314, it looks into memory, looks at the address 314, reads it into the accumulator. Zero-page addressing is a nice extra feature of the 6502, and a nice optimization. Anytime I want to read from memory, from the 0 page of memory, from the first 256 bytes, it can be encoded in just 2 bytes instead of 3, and it's also a little bit faster. If I load from 2, then it'll look at that address and read that into the accumulator. There's absolute X-indexed addressing, which is intended for reading from tables, from lookup tables. So it first adds X to that address that I specify and then reads from that address. In the example, I read from 200 plus X, so I read from 200 for 02OA, and 02OA is 52. I read that into the accumulator. Absolute plus Y, absolute Y indexed is the same thing with the Y register. I have, in this example, I would have an array of up to 256 bytes at that address. Zero page comma X is the same optimization with a zero page again. Note that whenever I do any zero page addressing or any index zero page addressing, it will always stay inside the zero page. So even in this example, if X is above 16 or above 15, it will wrap around to 0. The same is available with zero page comma Y. And you see in this example that this is a quite rare addressing mode. It's only available for 2 of the instructions. Zero page comma X indirect treats zero page as an array of pointers. So it first adds X to the address that I specify and then treats that as a pointer and reads from that address. So in the example, I look at the address 80 and 80 plus the contents of X, so it's 8C and 8D, so it reads that, which is C43F, little endian, which is the correct endianness anyway. And then looks at that address and reads that. Zero page indirect Y indexed looks the same, but it's different because it's first indirect and then indexed. So in this case, we only have one pointer at that address and then add Y to it afterwards. So we look at the address 14, and at 1415 we have D800. We add Y, we get D828, and then we can read from the address D828. Because we don't have a single 16-bit register, anytime we have to deal with pointers, we have to store that pointer in zero page and then use this addressing mode. If we don't want to do any indexing, we can always set Y to 0. And then there's register addressing, for example, the shift instructions for the accumulator and the decrement and increment instructions for registers directly work on those registers and don't need any extra parameters. There are register transfer functions between A, X, and Y, and you can also copy the stack pointer between X and the stack pointer. Speaking about the stack pointer, the stack grows down from 01FF. So if I push something, I load something, I push it on the stack, what happens is it stores it at the address of the stack pointer and then decrements the stack pointer. I store another one, so it stores it at the address and decrements the stack pointer. When I pull something from the stack, so I can push and pull the accumulator and the processor status, then it will first increment the stack pointer and then read from that address. Let's do it again, read it, increment it, then read it. The control flow instructions that are supported are jumps, indirect jumps. There's a jump to subroutine, which is a call. So if you know Motorola, you might be familiar with those memos. And there's RTS, which is the return instruction. What's interesting here is that the address that gets put on the stack is the current program counter +2, although a jump is 3 instructions. So when it gets read back from the stack, another one has to be added to get the effective address. This is a very interesting internal optimization of the chip. At the top of RAM, there are 3 vectors for interrupts, non-maskable interrupts, as well as the reset vector. The way interrupts work, we can see at the break instruction. Break is the same as an interrupt, but in software. It first pushes the program counter +2, just like in JSR. Then it pushes the processor status and then jumps to over the interrupt vector. You can distinguish between a software interrupt and a hardware interrupt in that you look at the status that got pushed on the stack. There's an extra bit, the break bit, which tells you whether it was software or hardware. And a return from interrupt will just pop the processor status and then pop the return address. So because there's no way to push and pull X and Y directly, this is what an interrupt handler would look like. If you want to save all the registers, you push your accumulator, you transfer X and push your X, you push your Y, you have to clear a decimal flag. Not everyone does it. I'll speak about the decimal flag later. And if you return from an interrupt, you pull Y, you pull X, you pull your accumulator, and you return from the interrupt. You can branch depending on 4 of those flags, on all those arithmetic flags, negative, overflow, 0, and carry, with branch plus, branch minus, and so on. Branch carry clear and branch carry set can be used for comparing comparing something for greater and for less. Like in this example, I compare something that I read from memory with 5, and if the carry is clear, which means it's less than 5, then it takes that branch. You can see that branches are encoded with a 1-byte relative address. So this is position independent, but you can only go up to plus 127 minus 128, counting from the byte after the branch. You can set and clear most of the flags directly. You can set and clear the decimal flag, which I'm going to talk about later. And if you set the interrupt flag, you will mask the interrupts and turn off all the interrupts. Setting and clearing the carry flag explicitly is necessary if you want to add and subtract, because it's only available with carry added as well. So you have to clear the carry flag if you want to add something, and you have to set the carry if you want to subtract something. So now about the D flag, the decimal flag, there's actually a patent on it. They had a very clever implementation how to do binary coded decimal, which nobody really uses, especially not nowadays, but it seems to have been pretty important back in the day. Normally, if you add 9 and 2 in assembly, you'd get OB. It's just a standard hexadecimal number. But if you set the decimal flag, it will do a decimal adjust after each addition and subtraction. So if you add 9 and 2, you will get a hex 11. This is how it's implemented, but that's not important right now. Let's talk about a very important instruction, which is the knob instruction. I tried to put everything that it does on a single slide, which is hard, but I tried it anyway. So now let's look at a small snippet of code. This code that I'm going to show you is taken from Commodore Basic version 2 from the PET update. It's written by Microsoft, and it's actually Easter egg code which will print Microsoft if you pass a parameter of 6502 to the wait instruction. So what it does, it loads, this is a 0-page load, the low byte of the first parameter, compares it to the low byte of 6502. If not, it branches away, tests the high byte, subtracts it, so if it's 0, it would also be okay. It's not equal, so we branch away. We store that, that's a 0, so we just initialize a pointer here. We also copy the 0 to the Y register. This is the high byte of the screen RAM address, so we store the screen RAM at parameter 1, so we can use that as a pointer in 0-page. This is the counter of how many characters in Microsoft. We load 1 character from the text. The text is actually obfuscated in a way that the upper bits are garbage, so we clear those upper bits, and we store it in screen RAM. Then we increment the pointer for indirect Y addressing, branch not equal for the loop. We increment the upper half of the pointer, if necessary. We decrement the counter for reading loop, and then there's another loop we can print Microsoft multiple times. So this code it's pretty likely that this code was written by Bill Gates himself. There's pretty good evidence that it was written by him, and if he can write 6502 code, so can you. Now, what's pretty important on the 6502 is cycle counting. If you want to apply it if you want to use the 6502 in any device, you will have to do cycle counting somewhere in any case. A rule of thumb there is every memory access will be 1 cycle, and there's no instruction that is less than 2 cycles. So let's look at that example again. Parameter 1 is a 0-page address, so if it had been an absolute address, it would be 4, but in this case it's 3 cycles, because load and parameter are 2 bytes already, and then it has the extra fetch of the 0-page byte, so that's 3 fetches. The compare is a 2-byte instruction, and it doesn't have an extra fetch, so it's 2. A branch is 2 bytes, so it's always 2. If it's taken, it's an extra cycle. This is another zero-page load. We've had that one, we've had that. What's interesting here is this is an absolute load indexed. Absolute loads are 3 bytes already, so that's 3 cycles. Then there's the load from RAM, which is the 4th cycle. And if we have a carry on adding X, then this is another cycle. So this one is 6. So some of them are a little more complicated, and the return instruction is 6 cycles, and so is jump to subroutine. The 6502 has several chip bugs that people have to work around. They have been fixed in later revisions, but this C64 only has faulty chips. It never got updated. And yeah, it's sometimes very important for compatibility that these are not updated. For example, if you have an indirect jump, it should read the address that it jumps to, the low byte from this address and the high byte from that address. But it fails to do the carry, so it reads the high byte from that address. So always avoid that instruction. This is an interesting quirk. Normally, you wouldn't notice it from a software perspective, but if you use it on memory-mapped I/O hardware, you can see the difference. If you increment something, it will do an extra store at the address of the original value before it updates it to the updated value. And there's something similar with a ghost read. If you store something X indexed, then there's another load at the original address, not at the address plus X, but the original address. So in this example on a C64, it would acknowledge all interrupts, even if it shouldn't touch that address at all. The break instruction can be lost if an interrupt occurs right there. So the break instruction is, yeah, better don't use it. And there's an interesting flaw in that there are lots of illegal opcodes, which are all the opcodes which are not defined, but they didn't bother to just set all those to knobs or to breaks or to crashes, but they just do a combination of all the other opcodes. For some of them, this means the machine crashes. For others, I have this table, so these are all combinations of at least 2 other opcodes. Some of them make sense. For example, store A and X into an address, so it ANDs those 2 and stores it in an address. That makes sense, and that can be used in software, and because on all C64s you're guaranteed that these work, you can really use them. And here's the second half of them. So let's talk about some tricks that you have to do on a C64 or on a 6502-based system. Because you're so register starved, you can only pass 3 bytes at a time to a subroutine, and you don't want to push them on the stack because the stack accesses are extremely complicated. You want to put your extra data onto the 0 page, and lots of programs do that. RTS jump tables are pretty nice if you need a jump table. What you can do is you load from the table, push it on the stack, and then just do an RTS. Of course, you have to the addresses you have to encode in memory are -1 because RTS adds another 1 before it jumps there. If you want to save RAM or ROM, and this is used a lot everywhere, including Microsoft Basic, you compare something in this example. If it's 5, yeah, then let's jump there, load something, and print that character. Otherwise, let's load something else, and now I would want to do jump print character as well, but that's 3 bytes. All I want to do is skip the next instruction. I could also do a branch not equal over the next instruction, but what I can also do is I can do .byte2c, which if I disassemble it and the branch does not get taken, decodes into a bit instruction, bit absolute, which just consumes the next 2 bytes. And a bit will just will AND that address with the accumulator and store it in the flags, but will not store it anywhere else. So it's basically a no-op for our purpose. So it skips the next instruction, and we only wasted a single byte. It's a little slower, but it's saved us 2 bytes. Self-modification is used a lot on 6502-based systems. In this example, which would clear the screen RAM on a C64, we could do this with 0-page indexed, 0-page indirect Y indexed, but it's a lot easier and even faster if we do it absolute Y indexed and then have an increment instruction that just increments this byte in our own code, if we're not running in ROM. Let's look at the block diagram again. Now we can understand a few parts of that. The program counter logic is pretty complicated. The cycle counter counts in which cycle inside the instruction we are, and this is the opcode which gets cached here. And these are the two fields that can get then passed into the instruction decoder. So depending on which opcode we have and in which state of the opcode we are, it outputs a few commands to the registers, which can either be put on the bus or taken off the internal buses, and it also controls whether the ALU, what the ALU is going to do. Looking at the die shot again, this is this decoder ROM. There's all this logic that controls everything, including the ALU, and that's the register set. The 6502 has about 4,000 gates compared to 20 or so million of today's CPUs. And you can see that about half of the CPU is registers alone, although it's just 4 or 5 general purpose registers, or 4 or 5 registers at all. The 6502 next to the Z80 has been a very important CPU. It has been used in many, many systems. For example, the Apple I, which is a rare collector's item today, the Apple II series, the BBC Micro. It's been in all the Atari 8-bit computers and gaming consoles and handhelds. It has been in the Nintendo 8-bit and 16-bit gaming consoles, and it has been in that guy, of course. The C64 uses a 6510, which is exactly a 6502 with just 6 more I/O pins for memory switching and a few other things, and it runs at almost 1 megahertz. So those extra pins that it has, it can switch memory on and off. The problem with the 6502 is that it can only address 64 kilobytes of memory. But the C64 already has 65 kilobytes of RAM, so what about ROM and I/O area? So this is the normal memory layout that you would see, but you can turn on and off all those ROMs. So underneath BASIC, there's another RAM bank. If you turn it off, you'll just see that one. What's interesting, if you write into ROM, it will always write into the RAM underneath. The kernel you can also turn off, and underneath the I/O area there's not just RAM but also the character ROM, which you can turn on if you want to modify the built-in character set and install that one. Let's look at the I/O area. It consists of memory RAM I/O for the video controller, the sound controller. There's an extra kilobyte of color RAM, which is external video RAM, which supports the video controller. And there's the two complex interface adapters and 2 more slots for extensions that you can put on the expansion bus. Let's look at the 2 ROM areas that we have. Kernel ROM sits right on top of hardware. It has the machine init and test code, so it owns the interrupt vectors. There's real-time clock emulation in there. It sets up a 60 hertz interrupt and then emulates a real-time clock on top of that. There's RS-232 library code, which you can use on the user port. There's a keyboard driver, there's a screen driver, the IC serial bus driver for floppies and printers, and there's a tape library code. On top of the screen and keyboard driver, you have a screen editor, which allows you to move the cursor freely on the screen. And if you press return on a line that was previously printed, it will feed that back into the input buffer. On top of tape and IEC, you have file I/O semantics, and on top of all those devices, you can see the device numbers there, you have a character I/O library. All this is exported through a library call interface in the shape of lots of a jump table at the very top of ROM. So one of these would be character out at FFD2, and now you understand the license plate. In an example how to program kernel, this is the Unix cat command. I just read a file to standard out. So I open a file at device 8. This is the file name. I say open. I set my standard in to that channel. Then I get a character, write it to standard out, which is still the screen. I read the status. Are we at the end of the file? Yes, we are. Then we close the file and we reset the standard in device. But who would want to write assembly code if you can write basic code? The basic interpreter in the C64 is based on standard Microsoft BASIC. Microsoft wrote a basic interpreter for the Intel 8080 in 1975, and they ported it to other 8-bit systems, like the 6502. It was licensed to many, many vendors, including Apple and Commodore. So the version 1 was used in the original PET, but it had so many bugs that that Commodore requested an updated version 2, which was then shipped in the PET. But from then on, they never went back to Microsoft and just did their own thing and extended the source code into version 4, which had some extra disk commands for the PET and later versions of V4. For the C64, they took the V4 code base and removed all the disk commands again to get it down to 8 kilobytes, but left the bug fixes in. So the C64 and the VIC-20 have the updated but stripped down Commodore Basic version. This is the instruction set of Microsoft Commodore Basic, which is pretty minimal. The orange ones are the ones that Commodore added for disk I/O. The functions are pretty interesting because there's a very good floating point library built in that can also be used from other assembly programs if you need floating point support. This is a very generic BASIC. It does not have any hardware dependencies other than a 6502 and calls out into kernel. So it doesn't do much more than standard I/O calls into the kernel. So in BASIC, you can use all this memory from 0800 up to A000, and the RAM bank up there cannot be used by BASIC and is especially intended for support code in assembly that you can put there. This gives you the 38911 BASIC bytes free. But there's BASIC, and it's not really user-friendly. There's a graphical operating system, GEOS, which looks like this. It's pretty much it's a quite exact clone of the original 1984 Macintosh user interface, with also pretty much the same feature set, which is quite impressive for a 64 kilobyte 8-bit system. Berkeley Softworks, the manufacturers of GEOS, also made some extra software for that, including GeoCalc, which is a spreadsheet application. GEOS was pretty slow. A database application, as well as a desktop publishing application. GEOS does not use kernel or BASIC at all, so it turns off all ROM, has its screen RAM, its damage backup screen RAM, a lot of code, some internal data, and there's some memory left for the application. And GEOS also has a kernel-style jump table there. But if you don't want to go through any libraries, but want to program the hardware yourself, you have to go through all those chips. So there's the complex interface adapter, there's 2 of them. They all have 16-bit general-purpose I/O pins, either input or output configurable per chip. Both have each 16-bit timers and a built-in time-of-day clock, which is not used by kernel. So the CIA1 is used by kernel for the system timer, and it emulates the clock on top of that, and also does the keyboard driver in the interrupt handler. CIA1 also handles the 2 control ports with its general I/O pins, and also does the keyboard. This is the keyboard matrix. The C64 has about 64 keys, so they fit nicely into an 8x8 matrix. One side of the matrix is set to output on port A, and the other one is set to input on port B. And now if I press right shift, I short that one connection. And if a driver then sets each of those outputs to 1, then it will see that here's the shortage, and we'll see that 6 and 4 are pressed, which is right shift. CIA2 manages the IEC bus as well as the user port. Then there's the sound chip, the sound interface device, SID 6581. It consists of 3 independent voices. Each voice, so this SID is very interesting in its design because it's an analog and a digital analog device. Most of it gets controlled by digital logic, but mixing, for example, is analog, and filters are analog, which provides some nice effects and is very hard to emulate. It has those 3 voices, and each of those voices can either be sawtooth, rectangle, sawtooth, triangle, pulse, or noise. The volume gets controlled by an envelope and by standard attack, decay, sustain, and release envelope, which you can define per voice. and there are the analog filters, low pass, high pass, or band pass. For extra effects and for special purposes, you can make use of ring modulators or oscillator sync. Don't ask me what all that means. I'm not a digital music person. But if you want to read all this, it's in a patent about the SID. One thing I know about the SID is how you do digitized music or sampled music. Because there's a flaw in the original SID, every time you change the volume control, the master volume control, which is a 4-bit register, it does a short click. So if you do that repeatedly, you can put anything on the speakers. So if you have your digitized music, you just have a big loop and put it into the volume register. This also gives you a fourth voice. So many musical pieces use that as typically as the drums, as an extra drum voice. What's a lot more interesting to me is the video interface controller, 6569. This is the PAL version. There's the NTSC version, which is the 6567. The VIC supports a 40x25 screen or a 320 by 200 graphics mode. It can address 16 kilobytes of RAM and has 16 built-in colors. This is the built-in C64 character set. There's two character sets. This is the uppercase character set, which is default, and there's a lowercase character set, which you can easily switch. The VIC has supports 256 different characters. Every character on the screen can have one of those 16 colors, and the character is 8 × 8 pixels. So these are encoded with a bitmap, ones and zeros, and each line is a byte encoded in character ROM. So if the VIC wants to find out what color a pixel on the screen is, it first looks at screen RAM. This is an index to a byte in the character set. And then if it's a 1, it takes it from color RAM, and if it's a 0, it takes it from the screen background, which is global for the complete screen. There's enhanced background mode. In this case, you only have a third of your character set, but you can have 4 different background colors, and also combine it with different font colors. In this mode, only the bits 0 to 5 of screen RAM are the index. Color RAM, same thing. But now the upper 2 bits of screen RAM are an index to 4 different screen background colors. You can turn on multicolor mode. It doesn't make much sense for text mode, but all those jump and run type games that are based on tile-based graphics use characters as their tiles, and they can have 4 different colors per tile. So in this mode, every pixel is not square anymore. It's twice as wide, and 2 bits encode 1 pixel. Screen RAM is still indexed to the character set, and 3 of the combinations are taken from this global screen background, and 1 of them can be freely chosen from color RAM. If you set the MSB, then you turn multicolor mode off per character. That's also possible. Then there's graphics mode or bitmap mode. This is a very early example by Commodore themselves, but you cannot only do the 320 by 200 in 2 colors, you can have multiple colors, but there are some restrictions. So if you look very closely at those graphics, you can see it's square pixels, yes, but if you look closely at that one, you might notice that if you put that grid over it, that every 8 × 8 square can only have 2 different colors. So this is encoded like this. You have 1s and 0s for those bits as well, so it's encoded just like character RAM. And if you have 0s, it takes it from screen RAM, so screen RAM is now unused because it all takes it from 8 kilobyte bitmap in memory. 0s gets taken from 4 bits from screen RAM, and 1s also gets taken from screen RAM, so you can have those 2 colors, each one out of 16. But there's also multicolor mode. Multicolor mode doesn't have square pixels again, it has twice as wide pixels. And if you look at the grid here, at the 4 × 8 grid, you can have 4 different colors per block. And 1 of the combination encodes the screen background, 2 are taken from screen RAM, and 1 is taken from color RAM. So all the tiles have to share 1 color, which is the screen background color, but you can choose 3 colors freely. Then there's soft scrolling. You can shift the the picture left and right pixel-wise, like this. The problem is if you shifted it right by 7, the next time you want to put the next character in there, but you already see that there's nothing there because it lacks the screen room for a 41st column. So what you can do is you can switch it into 38 column mode. And you can do the same thing vertically and also switch it from 25 row mode into 24 row mode. The Commodore 64 VIC supports sprites. A sprite is 24 times 21 pixels in size, and there's 8 of these sprites. 0 pixels are transparent, 1 pixels are the dedicated sprite color that you can choose freely per sprite. There's also, again, multicolor mode, 4 colors, and 00 is transparent. 1 combination encodes the sprite color, which you can freely choose, and 2 encode the global multicolor sprite colors, which are global for all the sprites. You can expand sprites horizontally, vertically, and both, which doesn't seem like it makes much sense because the resolution is so bad, but if you use it wisely, you can do pictures like this. So these sprites are, well, most of these are normal, but the bird up there actually consists of 2 Y-expanded sprites, and it doesn't look all that bad. Sprite priority. Sprites with lower numbers are on top of sprites with higher numbers, and you can choose sprite priority over background or background over sprites on a per sprite basis. If you write a game and you want to detect sprite collision, the VIC can do that for you. So every time 2 pixels that it draws overlap, it knows about that and will raise a flag in a register and can also cause an interrupt if you want that. Let's look at how memory is laid out. VIC can address 16 kilobytes of RAM. So in these 16 kilobytes, you can have 16 different locations for the screen RAM. It has to be aligned to 1 kilobyte. A character set is 2 kilobytes in size. You can have it at 8 different locations. The bitmap is 8 kilobytes, so you can have 2 different locations for the bitmap there. And the sprite is 64 bytes. So there's up to 256 different sprites that you can specify, but only 8 at a time. So the VIC addresses 16 kilobits at a time, and it doesn't have its own dedicated RAM. It uses the C64's main RAM. So there's 4 different banks, and you can switch between those banks and put your video RAM wherever you want. But you have to be careful because in 2 banks, which is bank 0 and bank 2, there's an area where you cannot address RAM, but every time the VIC addresses something there, it will see character ROM instead. So you cannot put your own data there, but if you want to use the built-in character ROM, you can use it on those banks. So let's go more into the internals of the VIC. So I told you that it has a resolution of 320 by 200, but this is only the visible part, but the invisible parts are just as important, especially if you want to do some tricks. So let's take away the monitor and look at the overscan area. This is the area that the VIC really draws, but there's even more. There's the HSync and VSync areas, which don't draw any pixels, but they're there in the timing anyway. I'll show that on the next slide. But the timing works like this. If the raster beam draws the picture, it will draw it from left to right and line by line, and the time of 1 character on screen is exactly 1 machine cycle. So the visible screen would be 40 cycles at 1 megahertz, and a whole raster line is 63 cycles. So this is how the raster beam would paint the picture. It goes from line to line, from left to right, and also in the HSync area, and then also in the VSync area. And the raster register, which is located at D012, is then updated. So if at this position, I just in the middle of a line change some register of the VIC, it will change immediately, and I can do some nice effects there. Like if I change the background color in this line, the VIC will start drawing a different background color in the middle of that line and continue drawing that. So if I do this on the whole screen up to the end of the screen, it will just continue with a white screen there. If I continue doing that, it will draw a complete white screen on the next screen, but if I turn it back off, I can have this for 1 frame. If I want to do this for every frame, and if I don't want to compare the raster register all the time, I can set a raster interrupt. So I set an interrupt at those red points. So I set it to the first red point first, so it draws this half picture, the interrupt hits, I change the background color. It now draws a white background. Then I set another interrupt, and it hits, and I set it back, so it draws the rest. This is done extensively in games. Like here, we switch between text mode and actually that graphic is text mode as well. It's tile-based mode, and I need two raster interrupts to do this screen splitting. Another example here is this uses at least 3 raster interrupts to do the 3 parts of the screen which scroll differently. And the demo we saw uses screen splitting a lot as well. But what's also interesting about this demo is it uses the area outside of the screen area in the border. So first there's the raster bars, which are pretty easy to do because all you have to do is change the background color and change the border color at the same time, then delay a few cycles until you're in the next line and repeat the whole thing. And there's extra graphics down there. That is a little bit more tricky. I'll show you that trick now. You remember that we can switch the screen between 24 line mode and 25 line mode, so this is 24. If we look at the bottom left of the screen, this is 25 lines, this is 24 lines. Now what we do is we set the screen to 25 lines, which would be here, and set an interrupt handler or set a raster interrupt at that red dot. So we let it paint the whole screen up to the red dot. Now we change the line where the vertical border would start up to this address. And now that trigger, when it has to turn on the vertical border, never triggers, so it just continues painting the screen. It does not paint any more characters because it's not programmed to do that, but it can paint sprites there. So while normally if you had sprites, that would be behind the border. If you use that trick, so you have to do that on every screen, every time it paints the screen. So in hyperscreen mode, your sprites will behave like this, and you can put lots of sprites into the vertical border. Many games make extensive use of this, like this game. This is the actual screen area. On the bottom, you have 8 sprites here, just for that status. And the top border, you have also more sprites. All in all, you have 21 sprites on this screen, so how is this possible? This is also pretty easy. You have several compartments of the whole screen and several raster interrupts, and you just reprogram your sprite registers for every screen several times. So in each of those compartments, you can have 8 sprites. This is called sprite multiplexing, and if you're really good at sprite multiplexing, you can either have a good sprite multiplexing routine which can position them anywhere on the screen and position as many as you like, or you can do something like this which just reprograms the sprites whenever they are painted. And this way you get very big sprites. In this example, this flicker is caused, I think, by the emulator. I think the original game did not have that flicker. Speaking about perfect timing, the timing of the VIC is pretty complicated, and you have to know about the timing to understand some of the tricks. So the VIC and the C6502 share the same amount of RAM, and RAM runs at twice the speed, so they can share it pretty nicely, because on every rising edge, VIC can access RAM, and on every falling edge, the 6502 can access RAM. Because the VIC needs to do lots of memory accesses for the screen, like this. It has 1 memory access per cycle, which is 1 memory access per character, to read the character screen data. So it does 40 fetches per line. But on every first line of every character line, it has to do extra fetches because it has to fetch the indexes from screen RAM. So there it has to do two fetches per cycle. This is possible with RAM, but in this case, the 6502 cannot access RAM anymore, so the 6502 is stalled in that time. If you look at the complete picture, so in all those lines, in all those areas, the 6502 is turned off and cannot do any processing because the VIC is using the bus. These lines are called bad lines, and the rule for the bad line is pretty easy. If the lowest 4 bits of the lowest 3 bits, actually, that's a mistake, of the raster register are the same as the lowest 3 bits of the Y scroll register, then it means this is a bad line. So normally you would have the bad lines there, the red X's, But if I have a restore interrupt at the red dot, and then always make sure that this trigger never hits, and always change Y scroll so that it doesn't cause the next bad line, it's possible to move down and up the rest of the screen, and it will just paint nothing there. So I can move the whole screen without copying a single byte of data. If we look at this picture that I showed you before, it uses many, many different tricks that I'm going to talk you through now. It's also mostly based on the idea of bad lines. First, let's look at this. There's obviously more than 16 colors involved here. The trick used here is interlacing. You have 50 frames a second on a PAL C64. And if you switch back and forth between two different colors, you might not be able to see the difference, especially if the colors are pretty close to each other. So you could get a purple here, which is different from the built-in purple, so you get an extra color. In theory, this would be 256 colors if you combine those. But of course, if you alternate black and white repeatedly, it will just flicker, and you don't want that. So maybe you get another 10 or 20 colors out of that. So this is the combined picture, and picture 1 would be this, and this is picture 2. On the complete picture, this is picture 1, this is picture 2, this is the combined picture. But even if you look at a single picture, if you look at a detail of that, and if you look at the tiles, an 4x8 block here has more than just the 4 possible colors. In this example, you can easily find 6 colors. The trick you can do there is, because 2 of the colors come from screen RAM, and you can change the screen RAM pointer whenever you like. But you have to cause another bad line so that it rereads the screen RAM. So you do this, you cause an extra bad line, so pretty much all the screen is bad lines, and it will refetch all those. And what you have in effect is not those 4 colors, but in every 4 times 2, you can choose 4 colors freely, with some restrictions though. This is called FLI, Flexible Line Interpretation. But there's more tricks used in this picture. There's a lot of border area used. So if we look at the complete picture, the bottom border, we know that already, that's hyperscreen. There's lots of X expanded sprites there. You can see that the resolution down there is not as good, but it's hardly noticeable. And there's also sprites on the left and on the right. This is done with the same trick with the horizontal screen size, but you have to be cycle exact this time, because it's only one single character that the screen gets shifted left and right. So you have to be perfectly cycle accurate there, and you have to do it in every line. So these are sprites as well, and on the top you just overlay a few more sprites to get that. Another trick you can do, if you cause a bad line in the middle of the screen, it will just start drawing the next line and fetch the next line in the middle of the screen. So this way you can shift the screen, also without copying anything. So normally with soft scroll, you would soft scroll the first 8 pixels and then copy your complete screen, which is great for a text mode screen, but with a graphics screen you don't have the time. This would take 2 or 3 frames just to copy the whole data. So you can just move it without actually moving a byte. This is called VSP, variable screen position. The game I showed you before, Mayhem in Monsterland, uses this. This is running in bitmapped mode. This is a multicolor bitmap, and it just horizontally shifts the screen and copies the new data on the sides. Another trick you can do is you can compress a line. This is called line crunching. If you just cause a bad line to make the next character line draw already without finishing the current line. If you do this 25 times in a row, you can compress the whole screen into 25 lines. So this gives you the opportunity to move anything up and down as much as you want. If you the problem is that you have lots of garbage on the screen. But if you turn on multicolor and extended background color, the VIC will interestingly always output black pixel on top of everything. So this will, you won't see the garbage there. But you can put sprites on that to work around the black bars. If you use that in a game, it will look somewhat like this. This is Fred's back. You have sprites up there, and you have a real bitmap down there with all the colors, and you can move that in all directions. This is called AGSP, any given screen position. Normally, if you want to do something cycle exact, like in this example, I wanted to change the screen color and then change it back, it flickers a little. It flickers because if an interrupt occurs, it always has to complete the current instruction, which can be an arbitrary number, or which can be a different number of cycles. So there's a trick that I can smoothen this, which is I have a restore interrupt, and then I set a restore interrupt to the next line, and set a different interrupt handler to that line. I acknowledge my current interrupt, clear the interrupts to make interrupts possible again, and then I do a few knobs, and then the interrupt will hit. And because it was a knob that the interrupt hit, so I know a knob is 2 cycles. It was either in the first cycle or the second cycle of the knob, so I'm pretty close already, so it's 0 or 1 difference. But then in my next handler, I do lots of knobs to go to the end of the current raster line. Then I load the raster register, compare it to the line afterwards, and if it's the same, I go to the next instruction. The trick there is that the branch, if it's taken, takes 3 cycles. If it's not taken, it takes 2 cycles, and I just do the load so that it will just do the trick for me and smoothen the last cycle, and so I'm always cycle exact, like in this example. So we've looked at all the chips now. There's the CPU, there's the CIAs, the SID, we've looked at the VIC, we've looked at RAM, ROM, and the PLA. The PLA is the one that does some memory management logic. Normally you would have this layout. You can turn off ROM, kernel ROM, basic ROM. You can also turn off basic and kernel ROM. There's a possibility to turn off everything. And if you have external ROM in your cartridge port, you can map that into your address space. You can map the other part so that it replaces basic, and you can map both in. There's another interesting mode, which is the Ultimax mode. The Ultimax mode was a gaming console based on the C64 hardware, which was only sold in Japan and is very rare now because it didn't sell well. It only had 4 kilobytes, or it had less than 4 kilobytes of RAM, and if you're in this mode, so it supports Ultimax cartridges, and if you put those in, that it will go into this memory layout. The tape connector is pretty straightforward. It only has a sense motor and read and write pin. Those go to the CPU's registers or into one of the CIAs. The ISC bus is a serial bus which daisy change drives. It has these connectors. Those 3 are the interesting ones. It has data, clock, and attention. The bus protocol works like this. It's not important to understand the details here, but the C64 raises the attention line and sends the command, which includes the drive's number, sends listen, unlisten, talk, and untalk to arbitrate the bus. Because the bus is so slow, because there was originally a chip bug in the VIC-20 in the 1541 disk drive, this protocol had to be done in software, and it's so slow that third-party manufacturers did extra extensions that ran a different bus protocol, like the Epic's fast load cartridge or the final cartridge, which were up to 20 times faster. The 1541 is the major C64 floppy drive. There's a second version of it. It works on 5¼ single-side double-density disks with 35 tracks out of the 40 possible ones. The number of sectors is different per track, and you have 683 blocks, which is about 170 kilobytes. This is what a track looks like. It doesn't use the index hole. It has sync marks, which is all ones, so it cannot use. So it has to encode the rest of the data so that there are no all ones. This is the header of a sector. There's another sync mark, and this is the actual sector data, GCR encoded, and there's the next sync mark. The directory format looks like this. The file system looks like this. There's the block availability map and the disk name, 16 characters, and also on track 18 are all the file names, which are 16 characters, which is pretty modern. This is what the drive mechanism looks like, and this is the electronics. It's a whole dedicated 6502 computer with 2 VIA controllers, with ROM, RAM, and a PLA. The memory map looks like this. It has 4 kilobytes of RAM. It has an I/O area with 2 VIAs. It has ROM. Interesting is the old Commodore drives had 2 CPUs, one for the bus and the file system, the other one for the drive mechanism. On this 1541, it was shared on 1 CPU. It switched between those 2. One wrote job code and the other one wrote back the error codes. There's also a double-sided version. There's a 3.5-inch version, which wasn't as popular because not as compatible. There was even a hard disk. There's memory expansions. There's freezer and speeder cartridges. There's 16-bit CPUs for the C64 with 8 megahertz and up to a megabyte of RAM. There's also the Super CPU, which has 20 megahertz, 16-bit, and up to 16 megabytes. Great for GEOS, great also for the few games that support it. These came very late. And this is the C64 DTV, which is a complete reimplementation of the C64 on an FPGA, which is very hackable. You can attach an IEC bus and a keyboard to it. So, what's next? Have you learned anything? Yes. Then please go and code a demo. And if not, but if you know about any other systems, please do a presentation on any of these other systems. I would be so interested in the internals of the Amiga or the Apple II or all those systems. Thank you.